So I am Sunny Gogar. I work as an application engineer within Intel's architecture and graphics software group. Today I'll be presenting this work we did on behalf of my colleagues. The work we did with for porting SPECFEM3D globe to data parallel C++. We use Intel's DPC compatibility tool to achieve this migration. Today we'll cover a brief introduction to SPECFEM3D Globe package, what it consists of, and how are we going to use as part of this work. I'll share a motivation why we even thought about migrating this application to data parallel C++. Then I will briefly introduce Intel data parallel C++ compatibility tool, discuss what is the typical workflow for migrating an application. And then I will close with some summary and some performance comparison. Right. So this is the one slide introduction to SPECFEM3D Globe. The SPECFEM3D Globe software package actually, it simulates global and regional seismic wave propagation. If you see on the right side, the software package itself consists of code for Fortran, MPI, C, and you will see some Ruby code, which is used for generating OpenCL and CUDA code using an automated tool called Boast. The official repo is as shown in the slide, and we are using a development branch for this work. So it has all the latest codes bits which are needed for SPECFEM3D Globe. Now, because a lot of work what we did was based on Intel Gen 9 HD graphics card, right? So we did select couple of workloads for an analysis based on the amount of memory it needs and the time it takes to simulate those grids. So 1D isotropic premises prem with 64 by 64 grid size is what we use as workload 1. And one of the common benchmark workloads for simulating more complex Earth, which is S362 ANI, was used as a second workload. But we did reduce the size of the grid to 80 by 80 to fit on a Gen 9 graphics card. Now, let's discuss why do even I care about data parallel C++? Because on the last slide, I mentioned that the code already has OpenCL and a way to generate OpenCL code. Then why do we need another implementation for achieving heterogeneity or using accelerators from multiple vendors? Well, one of the motivations which I found is that when I started experimenting with the OpenCL version of the code, I noticed that the solver time was okay, but I did take a lot of time to in data transfer. So as you see on the graph, we spend around like 140 seconds for workload 1 in solver time, but then almost an order of magnitude high or time was spent in some initialization step, which involves transferring buffers from host to device. Similar thing was also observed for our second workload. We spent less amount of time on solving or doing the simulation, but a lot of time was spent in data transfer. On further analysis, what we found out was that this time was spent in a pattern of data transfer, which you can see on the right hand side, where we have this lots of small buffers being copied from host to device, and this copy was in CUDA. It is done with the help of a CUDA memcopy 2D, which is efficiently implemented. But for OpenCL, the same is achieved using a loop across CL&Q write buffers. So what it does basically is that is the efficient implementation of CUDA memcopy 2D is done in OpenCL with this intensive or time sensitive loop. So if you see in this code, right, this nspec crust mantle is generally of the order of several thousands, and this is not the only buffer which is copied in such a way. There are like so many buffers being copied to the device in a similar way. So this was definitely one of the bottlenecks we observed with using the OpenCL implementation of this application. And at several places in the code, it is already it's an already known fact that this is going to be slow. So as one of the motivations, right, what we thought was, if we want heterogeneity with performance, that is portability with performance, then OpenCL may not be the ideal choice for SPECFEM3D Globe. So that was our first motivation, and to try something out different. And the secondary motivation for me was to test out Intel Data Parallel C++ compatibility tool on a workload which is more than a toy code, right? So that were my initial two motivations to move along. A brief introduction to Data Parallel C++ compatibility tool. This tool assists developers in migrating the CUDA source to Data Parallel C++ code wherever it can generate code. What I've seen with my experience is that the tool generates up to 80 to 90% of the code and migrates it automatically. For the rest of the code which is not migrated, it does leave good inline comments, which we call DPC or diagnostic messages. And uh, and uh, an example, there is a diagnostic reference I will cover later in the slides. What I want to cover here is a usual workflow which can be applied not only to SPECFEM3D Globe, but any application. So the process starts with preparing to migrate. So when you say prepare, a stage prepare, it includes a step called intercept build. As the name suggests, what intercept build does is intercepts the build process and logs some useful information in compilation database, what we call a compile commands.json file. This JSON file has useful information like the part to the include headers used in the code, some of the constant or compile time constants, and so on, which is used by the second step, which is the migration, to migrate the code automatically. So the second step is usually running the dpct command and providing it input the compilation database. Once the migration is done, the final and the most important step is to verify the code for correctness, and also manually complete the parts of the code which were not migrated by the compatibility tool. If I apply the same steps to SPECFEM3D Globe, the steps are as follows. We prepare the code by getting the source code as it is, and then we complete the configure step as you would do with the CUDA source code. That is, I configure it with the latest CUDA 9 branch of the code, and provide paths to the CUDA lib and MPI include headers. Now, this is the usual step you would use if you were compiling the code for CUDA. So there's nothing different here. As the third step, instead of just building, right, we start with intercept build and then pass the make command to it. In this case, I've given an extra argument -i to ignore all the errors, the make errors if you get, and just care about what are the compilation commands used to build this application and log them in a compilation database. So usually you can use the same steps, intercept build make -i, with any application, not just SPECFEM3D Globe. Once this completes, the preparation stage is done. We migrate the code with a simple step dpct and pass it to a compile commands or JSON file. So this step is the step where your CUDA sources are migrated to data parallel C++ sources, and they are outputted to a default directory, maintaining the structure of your or the directory structure of your application. And once this is done, final step, as mentioned, is reviewing all the diagnostic messages, what you see as part of the migrated source code, manually edit wherever the edits are needed. And then once you start compiling and running your code, you will obviously, you might see some of the not so obvious issues, and we need to address them correctly. I've been talking a lot about diagnostic references. So this is one example. I would want to show what a diagnostic message is. So every line of the code would have, wherever the diagnostic message are inserted, you will have the source file where this message exists, the warning message itself, and then there is going to be a diagnostic number, which usually starts with DPCT10, and then there is a code with, which is used, or which the code is used for helping developers so that they can complete the migration process. On the right hand side, what you see is the diagnostic reference guide, which the compatibility tool team maintains, so that developers can, when they see the diagnostic messages, they can understand the message, and the tool or the compatibility tool provides some suggestions how to fix those messages. So as you see, this diagnostic reference guide, it has like information for each of the messages, and how would a developer fix the message once they see this. For SPECFEM3D Globe, if I grep for simple DPCT10 and look at the number of diagnostic messages, what I see is that a lot of the messages or the migration diagnostic messages are with respect to error handling. Now in CUDA, the error handling is usually very intrusive in terms of every step. Developers tend to write a error handler, but with SQL, right, a lot of this error handling can happen asynchronous with the exception. So though CUDA uses the CUDA sources uses this in data parallel C++ code, developers can either catch the exception in each occurrence, or they can also rely on the exception handling of C++ to take care of error handling. We also saw a lot of diagnostic messages with respect to the APIs, the CUDA specific APIs. So certain things like compute capability device, right? The information about that, the device versions, certain device properties, right? There is no equivalent APIs in SQL. And so the migration tool does not generate any code for that when you are trying to print information. But in SQL itself, there are other ways to know information about the devices. So this portion of the code is usually something developers will have to migrate and edit manually. There was one more important thing I noticed was the use of atomics. So when the migration, the compatibility tool migrates the code which has atomics, it assumes that the atomics are global atomics by default. In case if your code is using shared local memory atomics or the local atomics, then in that case, an additional property will need to be manually provided to those calls. So this has to be reviewed and correctly implemented. And the last thing which I noticed important was that the work group sizes, the code assumes whatever the default work group sizes was set in the CUDA source code, that same size is assumed in or throughout the code. So for these kind of changes, you will have to validate the work group sizes to make sure that if you are running, for example, on a Gen 9 graphics, which has a limit of only 256 OpenCL work items or data parallel C++ work items, then they will have to be reviewed and fixed accordingly. So these were like some of the common known diagnostic messages which we can seek help from the reference guide and fix. But I did see some of the not so common issues as well, which were specific to this application. Now, one of the thing which I saw that this CUDA source code used function pointers in a couple of places. Now, though function pointers are being added now as part of SQL extensions, the compatibility tool has not caught up with that. So if you look at the migrated code, the function pointers were not migrated, and hence I had to manually rewrite the use of function pointers in a couple of places. Texture memory API was disabled in when we used CUDA 9, and for the devices Volta and newer, the texture memory API code was not used. It was disabled using a compile time variable, and hence when we migrated the code, I left that code as disabled, because texture memory API does not make a lot of sense with the Gen 9 graphics as well. GPU async copy was another variable I disabled because this relied on NVIDIA's device capabilities, like host memory mapping, right? So there is no equivalent functionality for Gen 9 graphics, and so that is why I had to disable the code for GPU async copy. It was a compile time variable, and disabling it was like as simple as turning a bit from 1 to 0. And to my surprise, there were some time logic in the code which did not migrate as I expected, and so I had to review and fix them as well. Now, if I compare the migrated data parallel C++ code and running it on an Intel Gen 9 graphics, I observed that the solver times more or less remain same when compared to the OpenCL version, but the overall wall clock time, which consists of the data transfer time of the small buffers, right? It reduced significantly. So this graph shows a logarithmic scale, right? And if you see for the workload one, the OpenCL version, which took around 3,600 plus seconds, the same data transfer took only 393 seconds with the data parallel C++ version on the same system with the same GPU and okay. Even for the workload 2, we saw similar thing. The simulation, the solver times were equivalent, close to equivalent, and the overall wall clock time for data parallel C++ version reduced to about 2000. So this points to us that because we were not now limited by the OpenCL's way of copying the small buffers, and by using data parallel C++ level 0, and the optimizations being enabled in data parallel C++, we were not limited by the data transfer time of the small buffers, and hence it's significantly reduced. So if I look data parallel C++ with the level 0 backend, right, it becomes more, could be a primary choice when it comes to achieving portability along with performance. And because it is SYCL, now we have the freedom to leverage other primary backends as well. So if I summarize what we did, the migration of 100,000 plus lines of code would have not been easier without data parallel C++ compatibility tool. It did significantly reduce the migration time of starting from CUDA source to data parallel C++ code. If you look at the migrated code, the MPI portion and the Fortran code, they remain untouched. And so what you basically have is a MPI plus Fortran plus CUDA code now migrated to MPI plus Fortran plus data parallel C++ code. The advantage is that now with data parallel C++ code, you have the freedom to support more different types of accelerators because it is SYCL. And SYCL enables developers to tap in performance and the new features which are all enabled with the primary backends like level 0 from one API. CUDA backend you can use with the data parallel C++ or the CLang C++ compiler, and with the ROCm as well, which is currently HipSYCL is being developed and it's a work in progress, but then provides you the ability to use SYCL source code, the same SYCL source code now on the AMD GPUs as well. So for me, to summarize, right, SQL was it felt like a better choice when it comes to achieving portability with performance to consideration. So this is some information about what version of the code I used and what were the workloads I ran to collect this information. And now I will open up for any Q&A if you have.
So there is one question from Nicholas. Is the small buffer data transfer time issue a problem with the DPC++ versus OpenCL, or is it more of a runtime plus driver issue?
It is more of an OpenCL implementation issue. Uh, the way OpenCL takes care of the small buffer copies, it issues a lot of several the messages are enqueued. So if you look at the CUDA implementation of this, right, the way it works is that you're depending on the pitch size, you will create a large buffer, and then a large mem copy happens for the big buffer. Similarly, if you look at the data parallel C++ implementation of doing a CUDA memcopy 2D, it uses this kind of optimization. But OpenCL by itself, it doesn't do this. And so this is more of a OpenCL implementation issue. But if you run this code with the OpenCL on an Intel GPU or OpenCL backend on a NVIDIA GPU, you will see a similar behavior.
So, yeah, yes, sir, thanks to you.